So for the 2019 free response part of the exam, okay, question number 1 deals with fish entering a lake and also fish leaving a lake, and they're giving you the rate E of t. Okay, so the rate E of t is the rate at which fish are entering the lake, and then L of t is the rate at which they're leaving the lake. Okay, and this is there. It's both are measured in fish per hour. Okay, and t is measured in hours since midnight, so t equals 0 would be equivalent to being midnight. Okay, so for question A, how many fish enter the lake over the although a 5-hour period from midnight to 5 a.m. So t equals 0 to t equals 5. Give your answer to the nearest whole number. Okay, so we need to integrate E of t because it's the amount of fish entering the lake. Okay, so let's do that, and we'll do that on our paper. And you also can use a graphing calculator on this to do the integration. So we want to integrate from 0 to 5 E of t dt. Okay, and we're going to put this into our calculator. Okay, now remember, E of t, the units on E of t is fish per hour. Okay, and d of t is hours. So if we take fish per hour and multiply it by hours, we're going to get the number of fish, right? So this is the total number of fish from 0 that enter the lake between 0 and 5. So we're going to go to our graphing calculator and put this in. So what you want to do is go press y equals, and you want to enter E of t. I would enter this because you're probably going to need this E of t in other parts of this question. So I would type in 20 for y1, 20 plus, and then 15, and then sine of pi t over 6. So 20 plus 15 sine of pi x over 6. Okay. And so let's go. I'm going to quit this and go to the home screen. And then what we want to do is we want to integrate. So number 4. And we want to integrate from 0 to 5 and y1 and x. Okay. So then this is going to give us 153.458. And they said give your answer to the nearest whole number. So this would be 153 fish. Okay. All right. That's how many fish have entered the lake between midnight and 5 a.m. Okay. So let's go back and record this on our graphing calculator, or on our paper. So this is equal to 153 fish. Okay. So we would say something like this: 153 fish entered the lake from midnight to 5 a.m. Okay, so let's go to part B and we'll answer that question. So part B asks, what is the average number of fish that leave the lake per hour over the 5-hour period from midnight to 5 a.m. Okay, so we want to know not the number of fish, but the average number of fish, right? So that's the average of the function L of t. Okay, so the leaving fish. Okay, so we're gonna do that. Okay, so we'll go to our paper and write that up. So for this one, what we want to do is we want to integrate. First, we want to do 1 over 5 minus 0. Integral from 0 to 5 of L of t dt. Okay, so this is equivalent to 1/5 the integral from 0 to 5 of L of t dt. Okay, and then we can put this in our calculator. All right, and we'll figure this one out. So we'll go back to the graphing calculator. So once again, we want to press y equals, and into y2, I would put the rate at which the fish are leaving the lake. Okay, so L of t is 4 plus 2 raised to the 0.1x squared. So 0.1x squared, like that. I'm just double checking to make sure I entered it right. Okay, and then we'll go to our home screen. And this time alpha x for the fraction bar, so 1 over 5 and then alpha window 4 for function integrate 0 to 5. And just be sure, okay, you put the rate at which fish are leaving in y2. So this needs to be y2. So alpha trace and then number 2 for y2, and then integrate with respect to x. And so 6.059, okay, that's the average number of fish leaving between midnight and 5 a.m. Okay, so we'll go back and record this on our paper. So this was 6.059, okay, and we would say the average number of fish that leave the lake per hour. Because this 6.059, I should say this, okay, so when we integrate, it gives us fish, and this would be fish per hour, right? Because the 5 is hours. So this is fish per hour. So it's giving us the average rate, okay? So the average number of fish that leave the lake per hour is 6.059 fish per hour between midnight and 5 a.m. Okay, and that's the answer to part B. Okay, so now moving on to part C. Okay, at what time t for 0 less than or equal to t less than or equal to 8 is the greatest number of fish in the lake? Justify our answer. Okay, so now we're talking about the overall number of fish in the lake, right? So we have to take into account the fish that are entering and also the fish that are leaving, okay? So the number of fish, the derivative of the number of fish in the lake is these two, E of t and L of t put together, okay? So what we're gonna need to do is, this is for the greatest number, they're asking you for the absolute maximum, okay? For the greatest number, that's also translated into absolute maximum, okay? So we need to find the relative maximums, okay? And then also check the endpoints, 0 and 8, to see how many fish there are and just see which one's the largest, okay? So the derivative of the number of fish in the lake would be E of t minus L of t, okay? And we're gonna set that equal to 0, okay? So let's go to our paper and we'll figure this one out. Okay, so the rate of change of the number of fish in the lake is this function E of t, is this new function E of t minus L of t, okay? And we wanna know when this is equal to 0. Okay, so we need to solve this, okay, and then we're gonna find the largest, well, we're gonna integrate this function, right, to get the number of fish in the lake, okay? All right, so let's solve this first with our graphing calculator. Okay, so what I wanna do is go to y equals, I actually wanna turn these off. I don't wanna graph these two. So I'm gonna go on top of the equals and turn those off. Okay, so if the equals aren't highlighted, then that means it's not going to graph it, okay? And y3, I'm going to make that green. Okay, I mean, you could graph all three at once if you want to, okay? It's just hard, and then just know the green one is the one that you're looking at, okay? So this would be y1, which is the amount of fish, or the rate at which fish are entering the lake, minus y2, the rate at which they're leaving the lake, which gives you the rate of change of the number of fish in the lake, okay? All right, so this would be alpha trace, and then y1 minus alpha trace y2. The time interval that they're giving you for this is 0 to 8. So let's go to our window and let's set our x min at 0 and our x max at 8. Okay, and I would probably, it's x scale 1, y min, let's just leave it negative 10 and 10, and y scale 1, and just see what we get, okay, from this. And obviously we didn't go high enough, right? Okay, so we need to go a little bit higher with the y max. Okay, so quite a bit higher. So let's go window, Y max. Let's go to, I'm thinking like 50. Okay, and now let's change our Y scale to 10. And graph that. Okay, and then let's also go to Y2, and let's go down and make Y4 be 0, because that'll allow us to solve it. Okay, so now graph that. Okay, so it's going to happen right here. Okay, all right, so the rate, okay, so from 0 to 8, okay, is the only time that this is positive, right? The derivative is positive. So that means the number of fish are increasing until this time, and then after that they're decreasing, right? So this is also going to be, this would have to be the overall maximum too, because we're changing from increasing to decreasing. And so this has to be it. From 0 to 8, we're increasing until this time, and then the function is decreasing, okay? So the rate at which it is, okay? Okay, so let's find this value right here. So second trace and number 5 intersect. Enter for the first curve, second enter, and then just guess. We're really close. So 6.204, okay? So let's go back and record this, okay? And let's also, you know what, I'm going to actually store this right now in the calculator, okay? So we're going to second quit, and then we're going to take X, and we're going to store it as alpha A. And now I don't have to type that in anymore. Okay, so if we want to use this for anything, we have it stored as A, right? Okay? All right. Okay, so let's go to our paper and record. Okay, so the solution to this was T is approximately 6.204. Okay, so let's calculate how many fish were in the lake at time 0. Okay, so that would be, okay, so this would be the integral from 0 to 0 of E of t minus L of t and then dt, okay? And then we're going to also integrate from 0 to 6.204, but really not that. It's going to be the whole decimal, right? E of t minus L of t dt. And then we also want to integrate from 0 to 8 of E of t minus L of t dt, right? Okay, so the integral from 0 to 0 is simply just 0, right? So we don't need to put that one in our calculator, but we are going to need to put these two in our calculator, right? And then we're just going to look at which one's the biggest, okay? All right, so let's go ahead and go back to our calculator and let's enter these integrals to see which one is the largest, okay? Okay, so we're going to go to alpha window, and we're going to integrate, so number 4, and we're going to integrate from 0 to this a value, right? So alpha a, and then y1, because that's the rate at which fish are entering, and then minus the rate at which they're leaving, which is y2, and then dx. And then we also want to go from 0 to 8, right? So actually, I'm going to go and just copy this and then just get on top of the A and type in 8. Okay? That'll be faster. Okay, so it's going to be this one, right? It's going to happen at this time A, 6.204. Okay? All right, so let's record these values because we need to show our work, right? This is part of justifying our answer, okay? We're going to show our work and then we'll write our answer. Okay, so from the calculator, this one, integral from 0 to 6.204, came out to be 135.015. And this one from 0 to 8 came out to be 80.920, really. Okay, and then this one's the largest. Okay, and the question was, at what time is the greatest number of fish in the lake? Okay, So we would just say the greatest number of fish are in the lake at T is approximately 6.204. Okay? And 6.204 hours if you wanted to put units on there. Okay? Slide it up a little bit so you can see it. The greatest number of fish are in the lake at T equals 6.204 hours. So that'd be 6 a.m. plus a little bit, a few minutes, right? Okay? About almost a fifth of an hour. Okay? All right, let's go to part D. So question D is the rate of change in the number of fish in the lake increasing or decreasing at 5 a.m., which is T equals 5? Explain your reasoning, okay? So the rate of change of the fish in the lake is this new function combined with the number of fish, the rate at which fish are entering the lake and the rate at which fish are leaving the lake, okay? By the way, this is an in and out problem if you didn't realize this, okay? So if we want to know if this rate is increasing or decreasing, we got to take the derivative of this new rate function, right? And so the derivative of E of t minus L of t would just be E prime of t minus L prime of t, okay? And we got to do this at 5, okay? So that's all we have to do on this, all right? We're going to use the calculator again. Okay, so what we have to do is we have to find E prime of 5 minus L prime of 5 and see what this comes out to be, okay? So if this comes out to be positive, then that would mean it's increasing. And if it came out to be negative, that would mean it's decreasing, okay? All right, so this E of t and L of t are together, when you subtract them, is the rate at which the number of fish are changing in the lake, okay? And then we want to know if that rate is increasing or decreasing. Okay, so let's go to our calculator and put this in. Okay, so we have to take the derivative, so we're going to go alpha, window, and then it's number 3. We want to take the derivative with respect to x of, and this is going to be y1 minus y2. So alpha trace, and then number 1, y1 minus alpha trace y2 at x equals 5. And so we get negative 10.723. Okay, so let's go back and record this, and then I'll explain the meaning of it. Okay. Okay, so this value, when we calculate on the calculator, gave us negative 10.723. Okay, so that's negative, right? So that means that it's decreasing. Okay, so the rate of change in the number of fish in the lake is decreasing at time t equals 5. Okay. All right. So the original question was, is the rate of change in the number of fish? Okay, so the rate of change in the number of fish in the lake is decreasing at t equals 5, comma. Okay, so why? It's because this came out to be negative, right? So because E prime of 5 minus L prime of 5 was less than 0, okay? All right, now you could actually lead with this, right? Because E prime of 5 minus L prime of 5 is less than 0, comma, the rate of change in the number of fish in the lake is decreasing at t equals 5. So you could write it that way too, okay? So that's question number 1 for today, and I want you to do this one, and hopefully, like, this is starting to click. Now, you may not get every part. Do not worry about that, okay? It's the AP exam is about showing your knowledge of calculus, okay? So you don't feel like you have to answer every problem, okay? Because they're doing this widespread of from difficult problems to easy problems because they're trying to get a feel of how much calculus you do know, okay? So some of the problems are going to be hard, some of them are going to be easy, and just do your best. That's all. Just do your best. Okay. All right. I wish you guys could see me. Like my hands are moving right now. Okay. All right. So let's go to question number 2 for the 2019 exam. And we'll do that one. All right. So question 2 from the 2019 exam, it deals with a velocity of a particle moving on the x-axis, and they're giving you a table. So this is a table problem along with it being a particle moving on a line type problem. Okay. All right. So for part A, well, and they tell you it's differentiable. I should point this out. They tell you it's differentiable function. Okay. And if they ever tell you it's differentiable, that automatically means for it to be differentiable, it also has to be continuous. Okay. All right. And then the units are meters per hour for the velocity. Okay. And they're using this subscript. Okay. A lot of times when they use subscripts for like velocity and position and stuff like that, is they're going to talk about two different particles somewhere. And you're going to use those subscripts to make the distinction between the two velocities. Okay. All right. Or accelerations or positions. Okay. All right. So the first question is, justify why there must be at least one time t for 0.3 less than or equal to t less than or equal to 2.8 at which v sub p prime of t, the acceleration of the particle p, equals 0. Okay. Meters per hour per hour. Okay. So on this interval, there has to be a derivative of the velocity that's equal to 0. Okay. And that's going to make sense. Okay. Because from 0.3 is 55 and 2.8 is 55. So when you subtract these, you're going to get 0, right? And this is really a question asking you about the mean value theorem. Okay. Is there a derivative of this function at which it equals this? And there is. Okay. So we'll just need to do a formal write-up on that. Okay. Let's go to our paper and do that. Okay. So they say that v sub p of t is differentiable. Okay. And because it's differentiable, it's going to have to be continuous, okay, on 0.3 to 2.8, okay? All right. So therefore, v sub p of t is continuous. Okay. Now I'm just going to add something that, to this. Okay. So it needs to use the mean value theorem, and I'm just going to go straight from the mean value theorem. Okay. We know that v sub p of t is continuous on the closed interval 0.3 comma 2.8 and differentiable on the open interval 0.3 to 2.8. Okay. And then we also know that v sub p of 2.8 minus v sub p of 0.3 over 2.8 minus 0.3. Okay, so this is 55 from the table, right? That's 55 minus 55 over 2.8 minus 0.3. Well, that'd be 2.5. So that'd be 0 divided by 2.5, which is equal to 0. So their average rate of change between 0.3 and 2.8 of the velocity is 0. That automatically means that there has to be a derivative somewhere between 0.3 and 2.8 that would be 0, okay? All right? So therefore, we could say therefore, by the mean value theorem, you can say MVT, okay, by the mean value theorem, I'm just going to put here MVT, there must be and I'm looking at this, there must be a t, comma, 0.3 less than or equal to t. You know what? Not less than or equal to, just less than 2.8, such that v sub p prime of t is equal to 0. Okay, and that's the write-up for this. Okay, so really they're looking for this. They're looking for that you have the average rate of change. They're looking for that you have the conditions to make this conclusion. So these are the conditions: that it has to be continuous on the closed, differentiable open, and then there has to be one, right? There has to be one in this interval such that the derivative is 0, because the average rate of change is 0. So there has to be a derivative that's also 0. Okay, that's the mean value theorem. Okay, guys, let's go to part B. For part B, I'm going to slide down a little bit. For part B, use a trapezoidal sum with the three subintervals 0 to 0.3, 0.3 to 1.7, and then 1.7 to 2.8 to approximate the value of the integral from 0 to 2.8 of v sub p of t dt. Okay, now what this is going to give you is the change in position between 2.8 and 0, right? So that's called displacement in physics, okay? Or in here it's called displacement too. Okay, so we're going to use a trapezoidal sum to estimate this. Okay, so let's go to our paper and do that. Okay, so we have the integral from 0 to 2.8, okay, and v sub p of t dt. Okay, so that's approximately, okay, and then we have to do trapezoids, right? So remember the two bases are the velocity values at 0 and 0.3, okay? So it's 1/2 times the height, okay? And the height in this case would be the difference in your x's, it's your delta x, right? So that'd be 0, it's the height of your trapezoid, okay? So it'd be 0.3, and then times, okay, and I'm going to write the formal notation here. It'd be v sub p of 0 plus v sub p of 0.3. Okay, and then plus 1/2. And the next one's between 0.3 and 1.7. So that would be 1.4. And then times v sub p of 0.3 plus v sub p of 1.7, and then plus 1/2, and then we're going to go from 1.7 to 2.8, so that'd be 1.1 times, and then it would be v sub p of 1.7 plus v sub p of 2.8. Okay, that's the formal write-up. That would not give you the answer point, okay? So the answer point would come in by doing 1/2 times 0.3 times, and now we're going to convert these to numeric values. So v sub p of 0 was 0, and then v sub p of 0.3 was plus 55, and then plus 1/2 times 1.4 times v sub p of 0.3 was 55, and v sub p of 1.7 is negative 29, so I'm going to write minus 29, and then plus 1/2 times 1.1 times v sub p of 1.7, which is negative 29, right? And then the velocity at 2.8, which is plus 55. Okay, I would stop here. That's an answer. Okay, so stop right here on your AP exam and you've got your answer point, okay? Even though we haven't cleaned it up, okay? Now, I'm gonna continue and I'm gonna actually clean this up, okay? So this would be approximately 0.3 times 55 divided by 2, and then plus 1.4 times, and then 55 minus 29, that would be 26 over 2, and then plus, and then 1.1 times, and again, this would be 26, right? Over 2, okay? And then we put that in our calculator. Okay, that's what I would do. Put it in your calculator, and you would get 40.75. Okay, and that's it for part B. Again, okay, I'm going to tell you, stop right here. Okay, just stop right here when you, because I know it's not, I know it's not normal. It's not what you're used to, but just stop right here. Once you plug the numbers in, you're done. Okay. It'll save you time because you can go to the next problem. Okay. And not worry about doing, mathematics in your head and making mistakes. Okay. Just write that. Okay. Perfect. Let's go to part C. A second particle Q also moves along the x-axis, so that's velocity between 0 and 4 is given by v sub q. So here's where the subscripts come in, okay? And it's 45 square root of t cosine of 0.063 t squared meters per hour, okay? Find the time interval during which the velocity of particle q is at least 60 meters per hour. Now, what does at least 60 meters per hour mean? That means greater than 60, okay? So, or equal to, so greater than or equal to 60 meters per hour, okay? Now, so we got to find this time interval in which this happens, okay? So we're going to have to solve this inequality. We're going to do it graphically with the graphing calculator, because what we need to do is we need to set this velocity function, okay? Put that in our calculator, and we need to look for where this velocity function is bigger than 60. So we're going to put this in our calculator and 60 in our calculator, and then we're going to see the intersection, and where the velocity function is bigger, that's where we're going to find our interval, okay? All right, so let's write this up, and then we'll go to our graphing calculator. So we need to write the equation or inequality we're solving, which would be this: v sub q of t. Okay, that's the name of the equation, right? And it's going to have to be greater than or equal to 60. Okay, now what we have is the function. I'm going to write the v sub q of t. For your AP exam, I would just write this, because they know from the question stem that they know what this is. Okay, so you can use the function notation to help you shorthand what you need to write. Okay, so this would be, I'm going to write this out formally. Okay, so 45 square root of t cosine of 0.063 t squared, and we want to know where this is greater than or equal to 60, okay? All right, so we're going to put this in y1 and this in y2, and we'll solve it, okay? Okay, so we want to press y equals, and then we want to type in our velocity function, right, which is 45, and then the square root of x, and then make sure you come out of the square root, okay? And then cosine, and then 0.063. And then x squared. And then we'll close our parenthesis. Okay, and then we want to know where this is 60 also, right? So 60. Okay, and then window, okay, we're only looking between 0 and 4, so let's make our x-min be 0 and our x-max be 4. Okay, x scale 1's fine. Y-min, we need to be, our y max needs to be at least bigger than 60. So let's go with 100, and let's do a y min of negative 100. Okay, and then y scale, let's go by 10, and let's just see what happens. Okay. Okay, so the blue is the velocity function, right? And so the red line is 60, so that we know the velocity is greater than 60 between this time right here and this time right here. Okay, so we need to find those. Now I wouldn't take the time on the AP exam, but I'm gonna zoom in on this a little bit more. I'm gonna use zoom box. Okay, this is just me being particular. Okay, that's all it is. So you don't have to be as particular as me. Okay, I'm going to press enter, and I'm going to work my way across. And that's actually probably even a little bit too high, but I don't want to take the time to adjust it again. Okay, so enter there. Okay, so it's in between these two values, right? So this is the velocity being 60. So the velocity is 60 or greater from exactly this time value to this time value. Now we're going to need to store these, okay? So we're going to go to alpha, and then trace to get the, not alpha, I told you wrong, second trace to get the calc menu, and then number 5, okay, and then enter, enter, and then enter, okay. Now we want to store this as A, okay. So I'm going to quit from the graph screen, okay, and I'm going to store this X. So quit, and then we have our X, and then we want to store it as alpha A, so we can retrieve it and use it again, okay. Okay, so we've stored it now. Now we can use A instead of X, okay. Go back to the graph, and then we have to press second trace to get the calc menu. So number 5 for intersect, and then we want to get this one, okay. So we're going to come over here and enter, enter, and then enter, and then this is our second one, right? So since we stored this one as A, let's store this one as B, okay. So second quit, okay, and then we want to take X, and now we want to store that one as alpha B. Enter, and then we have it, okay. All right, so let's go back and we're going to answer this question on our paper and tell the inequality where this happens, okay. So the answer to this inequality is 1.866, and that number we stored, right, is less than or equal to T, which is less than or equal to the B value, right, that we got. So that was 3.519. It's okay to write on our paper 3 decimal places, okay? But you realize when you use that to figure anything else out, you need to use all of the decimal places, okay? As many as possible, okay? And that's why we stored this, okay? All right, so we've done the first part of this, the question, okay? So I'm gonna go back to the line or the question and talk about that. So what we just did is we found the time interval during which the velocity of the particle Q is at least 60 meters per hour, and we have that time interval, right? We have that time between 1.866 and 3.519. Any time in there will give you the velocity bigger than 60, okay? And then the next thing is we want to find the distance traveled by particle Q during the interval when the velocity of the particle Q is at least 60 meters per hour. Okay, so we need those 2 time values because we're going to integrate between those, right? Okay, and to find the total distance traveled, we have to integrate the speed function, right? The absolute value of the velocity. Okay, now for AB, they're probably not going to ask you on the distance traveled, total distance traveled this year, because that's part of the questions that are part of the standards that are supposed to be taught in the next unit, okay. But I'm going to go over it just in case they ask it, okay, because it's still an integral problem, okay. And we're going to use a calculator for it, okay. All right, so let me go back to the paper and we'll write this up. Okay, so to find the total distance, what we have to do is we have to integrate, okay, from 1.866 to 3.519, and we have to integrate the absolute value of velocity v of t dt. Okay, so a little bit of explanation, and I don't know if I've done this. I may have already done this, so please forgive me if I've already told you. Okay, we're taking the velocity because if you move to the right or you move to the left, you've moved a distance, right? So what happens is if you move a distance to the right and you move a distance to the left, they could cancel each other out, right? But we want to total all of them. So if you take the absolute value, all the velocity is going to be completely positive or 0, right? It will never be negative. So then if you integrate this, right, then what's going to happen is you're going to get all the total distance traveled, because all the negative distance traveled now becomes positive, okay? Hopefully that makes sense, okay? Now, to do this integral, it's really hard to do it by hand. So we're going to do it in the calculator, right? And we're going to use A. We're going to integrate from A to B of this, okay? So I'm going to put in a little approximation, and then we're going to go to our calculator and put this in, okay? So let's go to the calculator. So we're going to go to alpha window, and we want to integrate, so number 4, and we want to integrate from this A value, right? So alpha A to the B value, which is alpha B. And we have our velocity function. Okay, remember we have our velocity function. It's y1, right? This is v sub q. Okay, so then we're going to come over here and we'll put in y sub 1 right here. So alpha trace number 1. Okay, and then we want to integrate with respect to x. You know what? Hold on. Back up. We got to take the absolute value of it, right? Okay, so we got to press alpha window and number 1 absolute value, and then alpha trace y1. Okay, there we go. Sorry about that. Okay, then dx. Because what we were going to get is the displacement, not the total distance traveled. Okay, that would be what I had in here when it was just y1 would just be the change in position. Okay, all right. When we press enter, we'll get the total distance traveled, which is 106.109 meters. Okay, so we'll go back to our paper and we'll record this. So this from our calculator we got this is 106.109. Okay, so between t equals 1.866 and t equals 3.519, the total distance particle Q traveled was 106.109, and I believe it's meters. Okay, and that's the correct answer for part C. Okay, so let's go ahead and go on to part D. So for part D, it says at time t equals 0, particle Q is at position x is equal to -90. So it's on the left of the x-axis, okay? That's its position at time 0. And at the very beginning, we were told up here, particle P is at the origin at time t equals 0, okay? So that's going to be important because we're going to need to use displacement on this next problem, okay? So using the results from part B, which is we found the displacement between 0.28, 0 and 2.8 hours for particle P, okay, and the function V sub Q from part C, approximate the distance between the particles P and Q at time t equals 2.8. So we need to find the position of each particle at 2.8, okay? So let's go ahead and write that up. Okay, so the integral from 0 to 2.8 of V sub P of t dt would be equal to the position x, okay, of particle P at 2.8 minus the position of particle P at 0, right? The difference between them, right? The change in position, okay? Now we know this is 40.75, right? 40.75? Yeah, 40.75 is this integral, and that's from part B, okay? So I had to look it up in my answers. So 40.75 is equal to x sub p of 2.8, the position of particle P at 2.8, minus, now this is 0, right? Because at that, what we just said is the particle P is at the origin at time t equals 0. So at time t equals 0, position is 0, right? Okay, so what this is giving us is position of particle P at 2.8 is that the particle P is at 40.75, okay? Now we need to do the same thing for particle Q, okay? So over here, I'm gonna write, okay, so particle from 0 to 2.8, V sub Q of t dt would equal x sub Q of 2.8 minus x sub Q of 0, okay? And then we know this one is -90, right? Okay, so that means the integral from 0 to 2.8 V sub Q of t dt is equal to x sub Q of 2.8 minus -90, right? That's plus 90. And then when I'm going to move it over here, right? And so it's going to be minus 90. So this integral, actually, I'm going to write -90. I'm going to write it in front. I think it'll be easier to see then and put it into our calculator, okay? Okay, so when I move this over, it's going to be -90 plus the integral from 0 to 2.8 V sub Q of t dt, and that's going to equal the position of particle Q at 2.8, okay? All right, so x sub q of 2.8 is going to be approximately, and then we're going to put this into our calculator, okay? And we'll have it figured out, okay? So let me go to that. Let's go to our calculator and do this calculation. So we want to type in negative 90 and then plus, and then alpha window function integrate number 4, okay? And we want to go from 0 to 2.8. Okay, and this was y1, right? Let's just double check. Y1, yeah, that was the velocity of particle Q. Okay, so get back over here, a little too far, and then alpha trace for the calc menu, or alpha trace to get the y1 menu, and then dx. Okay, so this one's at 45.937, right? So if we find the difference between these, right? So I'm going to take that answer and subtract the position at particle P at 2.8. So I'm going to take my answer. So I'm going to minus, right? Because it'll take the answer. And then minus 40.75. And we'll know the distance between them, okay? And so the distance between them is 5.188 meters, okay? So let's go back and we'll record all this on our paper. So this position, right, from our calculator, we got was 45.938. Okay, and then we took this position, right? All right, and we took x sub q, 2.8, minus the position of particle P at 2.8. And on our calculator, all right, we got 5.188. And that's the distance between them, right? Okay, so, and let's write the question up. Okay, so it asks approximate the distance between particles P. Okay, at t equals 2.8, the distance between particle Q and particle P is 5.188 meters. Okay, and that's the answer to part D, and we are done with another problem. Okay. All right, you guys, that's it for today. I just want you to do these two problems and we'll be good. Okay, you guys have a good day. Take care. Bye.